Hi everyone and welcome back. I was always curious to understand more about Metasploit payloads. In this and the following couple of episodes, we'll look under the hood of Metasploit Encoders. Let's jump in! We'll start in this part with the dynamic XOR encoder. To make the analysis easier and allow us to focus strictly on the encoders for now, I've chosen a very simple payload to play with. A message box shellcode for Windows x86 platform. Unless I'm not missing anything, this payload only supports x86, but it's not a problem because we want to focus on the encoding part. I have a mini cheat sheet here with useful Metasploit commands and flags, listing payloads, encoders, options, and so on. Let's try some of them now. Since we're going to talk about encoders, let's first list all the supported encoders at the moment. This command is very useful because it provides information about the encoder's reliability. Check the rank column here. Some of them appear to have excellent reliability. If possible, we definitely want to use some of those. I'll start with the dynamic XOR encoder because I think it's a good learning example. It has a rating of normal. We're not sure yet what this means, but the best way to find out is to actually analyze it. We can use msfvenom tool to generate executables with the format exe, flag, and minus out parameter. Cheat sheet linked in the notes. Depending on the case, we can also generate the shellcode in a C string array format and embed it directly in a wrapper file for analysis. To see that it's working as expected, let's start with the first command to generate an exe and test it. I'll copy-paste this to save some time. Another very useful command is this one over here, which allows us to disassemble and see all the bytes and instructions from the shellcode. Some potentially useful information here, like the exe and so on. Sometimes we might just want to quickly look at the disassembled instructions from the shellcode to get an idea about what it does. So this is the shellcode itself before applying any encoding. Watch the prologue because it's something we're going to see later for other payloads. Let's apply the dynamic XOR encoder and specify the format raw so we can pipe it to the disassembler. We will focus on the encoding and decoding process in these episodes. We can immediately notice that the last portion of the shellcode looks gibberish, and that's because, as expected, it has been encrypted using the XOR algorithm. The first part of the shellcode contains the decoding stub, which we'll analyze more in depth in a bit, using a C code wrapper. Also, if you're curious about the actual Ruby code from Metasploit that generates this payload, you can search for it and examine it. The quickest way is using the locate command with the encoder name plus the .rb extension. Let's see what we find. Copy the full path and open it with a text editor. If we compare, we should see the same instructions we've seen previously in the prologue of our generated payload. Notice right in the beginning a trick we've seen in many other episodes. A jump to a call instruction at the end of the stub. The call puts the address of the next instruction on the stack, which gets popped back into EBX register in the beginning of the stub. We're pretty sure now that what follows is the XOR, the decryption routine. How can we analyze this easier? One way is to generate C code and play with it in a debugger. Let's see. The command will generate an array of bytes that will incorporate in C source code. This is a very useful trick we've seen in other contexts as well, to dynamically explore blobs of code. Here's the array output from msfvenom, already formatted and ready to be pasted. Back to the code. I won't insist much on the source code because we've seen this in many other episodes. Now we're mostly interested in the decoder, the first part of the shellcode over here. Let's compile and analyze it in IDA Pro. Compiled successfully. Here are both files, the exe generated from Metasploit and our wrapper. Both of them should work and produce a message box. We see a command prompt window coming from our wrapper code, but that's expected. I have already analyzed it in IDA Pro and commented the interesting parts of the code. We'll start by locating the main function, and the quickest way is based on the error message string. Cross-reference that and we'll land straight into the main function. We can spot the code to allocate memory using virtual alloc, the memory copy operation, and then the call into the shellcode bytes. Rename this for convenience, so we know it's the function pointer into our encoded shellcode. This is the offset to the shellcode. Let's rename it 2. Double-click on it. Since it's a short one, I've commented all the lines to understand what's happening. Remember, the decode is dynamic XOR with variable size key. As we'll see later, in our case the key is only 1 byte, but let's go step by step and understand what's happening. I've renamed some labels as well, by the way. The first instruction is a jump to a call. The call will insert the address of the next portion on the stack. This is a very important bit. The address is then popped into EBX register and moved to EDI. The AL register holds the marker for the end of the decryption key. CLD clears the direction flag in preparation for the next instruction, which will read a byte from the shellcode and compare it with AL, which is 8A. Let's also enable IDA to show us the raw bytes corresponding to the assembly instructions. We can set the number of the op code bytes in the General Settings Disassembly tab. The scan instruction will search until it finds the 8A byte, which is actually the second one here after the call. It represents the marker for the array that contains the decryption key. Following that, the ECX will contain the beginning of the encrypted shellcode, this one over here, starting with D6. The rolling XOR loop takes 1 byte at a time from the key array in ECI and XORs that with a byte from the shellcode pointed to by EDI. Notice the key is actually 1 single byte and the decryption happens in place. Then there is another marker for the end of the shellcode itself. This time it's 2 bytes. FD29 hex. Let's validate. As expected, these are the last 2 bytes of the shellcode. Another jump moves over to the next byte from the key array. Take a minute to study this if you will. In our case, looking at the marker for the end of the key array, the key is just a single byte. Okay, let's run this live in the IDA debugger. Jump into the shellcode with F7. Notice the address of the memory location is different from the one we've just seen. Remember, that's because the code was copied into a newly allocated block. First, convert this data to code. Take the jump using F7. Notice the key array ending in 8A and next the encode shellcode instructions. They will be modified and XOR dynamically. Let's see a few of them step by step. Watch the bytes over here, how they change as we loop through the decryption routine. This is a very simple but efficient idea. Add a breakpoint after the decryption is complete and press F9. Looking at RCX, it contains an address ending in 2C, which seems to fall right in the middle of an instruction. What's happening? Because the code looks gibberish, convert it to data and back to code, but just from the offset in RCX. If you remember, the initial 2 bytes represent the key byte and the end of array marker. Then convert the rest to code. This represents the actual shellcode that we've seen when we generated the raw version with msfvenom. Let's go back to the Kali VM and check. The raw version of the message box shellcode ends in FF5508 and starts with D9EB. That's pretty much what's happening. If we take the jump and let the shellcode finish, we'll get the message box. I hope this video clarifies what's happening behind the scene in MSF encoders. The first encoder is a simple XOR with a dynamic key. In the next parts, we'll dive into more interesting encoders. Thank you very much for watching and see you in the next episodes. Cheers!